Hello everyone, my name is Firas Hendele and this is a quick presentation regarding the REU project for 2018. This should give you a little bit of background about the classification problem of the seven-dimensional solvable Lie algebra. So let's just get started. What is a Lie algebra? Maybe we have never seen one of those before, but technically you did. If you've seen a vector space from your linear algebra class, a Lie algebra, basically we're going to be working with the finite ones. It's just a finite dimensional vector space. We call it G. And this vector space is very, very special. It has an extra tool coming with it, and that tool is called the bracket. And later we will call it the Lie bracket, but simply the bracket. Now this bracket is just a binary operation from G cross G to G. So it just basically acts on two elements of the algebra and spits out another vector. So the properties of this bracket, basically, we want this bracket to be bilinear, which basically means that it's linear in the first component and also linear in the second component. We can distribute the scalars out and just use the brackets on the elements of the vector space. So we usually denote the elements of the vector space with capital letters and elements from the field by lowercase letters. So it's bilinear, it's linear in both components. The other one is also skew symmetric, so if we change the order of the vectors, we basically pick up a minus sign. Well, this might start to sound something familiar, but the most important property, I would say, is the Jacobi identity, and this is kind of a triple sum with the cycle with xyz, yzx, and zxy. If you take that sum, that has to be 0 no matter which xyz you choose from the algebra G. And so if you look at this definition, we know a famous vector space, which is R3. You've seen that in your Calculus 3 class, and or vector analysis class. And we know a linear operation on the vectors, right? We've known the dot product as a binary operation on the vectors, but that one does not produce a vector. So the other one that we know is the cross product. Well, the cross product is certainly a binary operation. One can see clearly that it is a bilinear on the vectors, but is it skew symmetric? Well, if we change the cross product from x cross y to y cross x, we certainly pick up a minus sign. Now, the last thing to check if that cross product does satisfy the Jacobi identity, meaning that if you take x cross y and then bracket cross z, and then you add y cross z, and then bracket those two together, and then cross with x, and so forth, you're always going to get a 0 for the sum for R3. And so I'll leave this as an exercise for you to check that certainly it will satisfy the Jacobi identity no matter what xyz you choose in R3. So the first example of a Lie algebra that you've seen before is the space R3 with the cross product on it. So that gives you a Lie algebra of dimension 3. And another Lie algebra is basically the space of n by n matrices where the entries are coming from the reals. That's also a Lie algebra. We just need to specify, we know that it is a nice vector space, and the basis for this space is basically n squared matrices where you have 1 in each component and then zeros everywhere else. So this space is definitely a vector space. But the question is, what is that bracket relation? So to define the bracket relation on the n by n matrices, we basically look at this, what we call the matrix commutator. Maybe you've seen this before. So if we define the bracket of A and B to be the product of the matrix A with the matrix B minus the matrix B times the matrix A. And so we know that matrix multiplication is not necessarily commutative, but when those two matrices commute, then we get that this bracket would be 0. And so this commutator basically is a test to see whether the two matrices commute or not. So if they commute, you get a 0 bracket. And so we notice that the bracket of any matrix with itself is 0. And if two matrices commute, the bracket is also 0. And also we certainly, if we change the order of the bracket, we pick up a minus sign. And finally, I'll leave this also for you as an exercise to check that it is bilinear. And because it's matrix multiplication, scalars usually go out, so that's not going to be a problem. But the Jacobi identity is what's there left to check for you. And I remember, as a student, my professor gave this to me as an exercise to double check that, just to get your hands onto this topic and see if you can understand what the Jacobi identity is about. Let's take another example. Let's look at this space that is generated by three of the 3x3 matrices. This is called the Heisenberg algebra. And so if you look at any linear combination of those matrices, that's going to span the 3x3 matrices that are strictly upper triangular, because you either get one here or one here or one here. And so you'll never get anything on the diagonal and anything below the diagonal. Those matrices do span the upper triangular 3x3 matrices. And so since there are n by n matrices, and we define the matrix commutator, then we know that they define a Lie algebra. So now let's look at the Lie bracket on all possible pairs. So if we calculated the Lie bracket on all possible pairs, this is what we basically get. And so we get everything 0, except when we bracket H1 with H2, we get H3. And obviously, because it's skew symmetric, that's obviously going to be also negative H3. So to basically define what the Lie algebra is, we only agree to display by convention the non-zero brackets, and we do not, in order to reduce redundancy, we assume skew symmetry. So I would basically say that the non-zero brackets between H1, H2, and H3 is H1, H2 equals H3, and that basically, in mind, we keep the idea that H2, H1 is going to be negative H3, and if there is a bracket that you do not see on this list, like this one, for example, or this one, we immediately understand that it is going to be a 0 bracket. So, another definition here, we have the derived series. So if you look at any Lie algebra, we define the derived series by the following. The first element in the series, we take all the elements in G, bracket them with themselves. That's basically what appears on the right-hand side of this listing here. And so that is the first one. And then the second one, we take whatever came out from here and bracket them with themselves. And we keep going until this series terminates. Sometimes it does terminate, sometimes it doesn't. But when it does terminate, at some point, it doesn't matter when, but if it does terminate at some point, we say that this algebra is solvable. So here's an example. This algebra is a 4-dimensional. It's spanned by E1, E2, E3, E4, and the non-zero brackets are defined as follows. So again, since you do not see E1, E2, E3, that means that this bracket is 0. So those are the only 0 brackets. The first element of the derived series is that we look at G bracket with G, which is basically the right-hand side. So G1 is spanned by E2 plus E3 and E4. The second element in the derived series, we take those elements and bracket them with themselves. But if you notice that the non-zero brackets involve E1, and E1 does not appear here, so G2 is definitely going to be 0, because E1 is not in here. And so this is called this 4-dimensional standard solvable. Obviously, it is a solvable algebra. Another example is the special linear algebra. It is spanned by x, y, and z, and those are the non-zero brackets. So is this solvable? Well, let's take a look. We find the first element in the derived series, and that is the right-hand side. So obviously, it's spanned by x, y, and z, and then we bracket x, y, z with x, y, z, and they will come out x, y, z, and so on. So this series will never terminate, and so it's not solvable. The next definition is the lower central series, and basically we look at the first element of that series is when we bracket G with G, and so that's the same. But the second element, we bracket whatever came out here with the whole algebra. So that is the big difference here. And so we continue in this fashion and see if this series terminates or not. If it does, then we call this algebra nilpotent. Otherwise, it is not nilpotent. So here's an example. This is the 2n plus 1, so that's an odd dimensional Heisenberg algebra. Its non-zero brackets are the following. So we take E1 with En plus 1, and that's give you E0, and E2 with En plus 2, that's always going to give you E0. So the right-hand side is always going to be E0. So when we bracket G with G, it's just going to give me E0. But as you can notice, then I'm going to take the whole algebra and bracket it with E0. Well, E0 never appears on the left-hand side. And so when we try to find G2, G2 is just going to be 0, and so this is definitely a nilpotent algebra. Another example from Euclidean geometry is the Euclidean algebra, which is spanned by 3 rotations and 3 translations. This is a really nice topic. We can talk about it later. But the non-zero brackets are spanned by those 6 bracket relations. And as you can see, everything in this algebra, in those brackets, appear on the right-hand side. T1, T2, T3, R1, R2, and 3. And so if I try to find G1, I get the whole algebra again. And if I bracket the whole algebra with G1, that's going to give me the whole algebra again. And so this series will never terminate, and so this algebra is not going to be nilpotent. Well, one last definition is the ideal, and this is probably something familiar that you've seen in your modern algebra class. If we look at the subalgebra, we call this subalgebra ideal if we take all elements from the algebra and all elements from the subalgebra. Whenever we bracket element from that ideal into something from outside the ideal, we will always land into that ideal. And so here is an example from something that we classified before. And so if you look at the non-zero brackets here, all the non-zero brackets involve, on the right-hand side, E1, E2, E3, E4, E5, E6. So no, and all the non-zero brackets must involve E7 on the left-hand side. In other words, the elements E1 through E6, they commute with each other because they do not appear on the left-hand side. Also, whatever you bracket with E7, whatever you bracket E7 with, you will always get elements from E1 to E6. And so you can see that E1 through E6 is an ideal in this case. All right, and so what we need now, we're back to our title, which we need to get to, which is the nil radical. So as you can see here, part of our title is the nil radical. So the nil radical basically is the maximum ideal in G that is nilpotent as well. So the maximum nilpotent ideal. Going back to our example, we already agreed that E1 through E6 is an ideal. Well, is it nilpotent? And so to do that, we need to check the definition of nilpotent as before. I'm going to let you check that and verify that E1 through E6 is indeed a nilpotent ideal. The reason why it's maximum nilpotent is because if we go to E1 through E7, this algebra itself is not nilpotent. In fact, we just proved that it is solvable. So it is maximum nilpotent. E1 through E6 is maximum nilpotent because you can't go higher dimension than E1 through E6 and still be nilpotent. So that is the biggest nilpotent ideal, and so that's what we call the nil radical of the algebra. All right, so this still might be new concepts to you, but in time you'll get used to them. And so we have a theorem that says if you have a n-dimensional algebra, then the dimension of the nil radical has to be at least n over 2. And as you can see, the total of the product is the 7-dimensional algebra. So in dimension 7, the dimension of the nil radical could be dimension 4, 5, 6, or 7. So we have big 4 cases here. Well, let's take a look at some good news here. The 7-dimensional nilpotent case, we call them the nilpotent algebras. Those were classified by Seeley 93 over R, and by going in 98 over C. So this case here is done. The case where the uh, nilpotent ideal is of dimension 4, we've done that, me and my collaborator Gerard Thompson from the University of Toledo in 2008. So we have the case 4, case 7 are done completely. And so what this project is about is looking at the 6-dimensional nil radical case. Okay, so we are looking at this one. All right. And the 5-dimensional one is still an open project, which we did not get to yet. So this is a long-term project. And so we're going to focus on the 6-dimensional ideal. In order to focus on the 6-dimensional ideal, we need to start with 6-dimensional potent algebras. And so that is going to be going into 32 cases. We've done a few of those so far. So I'll give you a summary of what we have so far and what's left to be done. And so the first one is the 6-dimensional trivial nilpotent algebra. This was done with Carl Ferguson in 2014, and the results look like this. And so the classification, basically, we would like to get a table that includes all the non-zero brackets. And as you can see, we are already going to start with something that is 6-dimensional, that we already know what the bracket relations are. So we already know what the bracket relations on the 6-dimensional. The only thing that's left for us to do is to find the bracket with the 7th dimension that we're introducing. It's like kind of an extension. Think of it this way. So this is the 6-dimensional case. And then a Heisenberg plus R, this is a 3-dimensional algebra. The 3-dimensional algebra as well, that's trivial. So this was done in 2015 and by Christopher Mattoon. And then the 4-dimensional algebra of order 1. So this is the first one in the list in dimension 4, plus the 2-dimensional trivial. This is still not done. The algebras A51 through A56, those are 6 cases. So those are the first 6 5-dimensional algebras, and then you are going to kind of do a sum with R. So this is a 1-dimensional. So together they're going to make a 6-dimensional nilpotent. All right, so we have done 2 of those cases. The first one was done by Bertschinger, Kosten, and Mattoon in 2015 as well. And those were the results. And the second one was done by Anthony Pecoraro in 2015. So 2015 was really a good year. And so what's left are 4 cases from this one here. And also there are 22 cases of 6-dimensional. Those are the 6-dimensional potents. There are 22 algebras here. I have done 6 of those this summer. So we still have plenty of cases here. And finally, a 3-dimensional Heisenberg plus a 3-dimensional Heisenberg algebra. So those together are all 32 cases. And as you can see, we've done a lot of work so far. We have finished like 10 cases of those, and we still have a few to go. So the idea is to classify the algebra, we need to find all the bracket relations between all the algebra basis elements, E1 through E7. And so we already know what the bracket relations between EI and EJ were I and J from 1 to 6. Those are already well known. Okay, so the only thing that is left for us to do is to know what is the bracket relation with EI and E7. And as you can see, this should be a linear combination between all the E's. But we do not see E7 here. Now the reason why we don't see E7, because we want E1 through E6 to be an ideal. So we cannot see E7 on this side. And as you can see, the only unknowns are those constants here, the ones in red. So if I ask you how many unknowns do we have? Well, I goes from 1 to 6, and so those constants, there's a line for each I, and so those are 36 unknowns. We find those 36 unknowns and our algebra is classified. Very simple. It's just tracing down 36 unknowns. This might sound like it's a very difficult task, but we have a lot of good tools and programs that we can use that will make our life a little bit easier. So we put those 36 unknowns in one matrix, and we call this the adjoint matrix. This is kind of stripping down the problem and just looking at the DNA of the algebra. So if we can find those constants in this matrix, the 36 constants, we're good to go. I hope you're on board with this project. If you like what you've seen, if you'd like to know more, please feel free to contact me. Thank you for watching, and hopefully I'll see your application with the RU materials. Thank you.